is basically the matrix Q, where Q transpose Q equals to Q transpose equals to identity. And we have learned another matrix U transpose U equals to U transpose equals to identity. So in this particular case, Q is called the orthogonal matrix. And this particular thing, U is called the unitary matrix. So they are interchangeably used in quantum computing. They are even sometimes the unitary is used. The orthogonal is also used same as the unitary context. But the only difference is that the component of Q, that is the Qij, they are coming from real numbers, and Uij, so that is the elements of the matrix U coming from the complex numbers. That's all. So transpose or dagger. Okay, fine. You take star. Sometimes I write this. You can tell mistakes as well. So star is basically complex conjugate. Complex conjugate transpose. Right. And this is only simple transposition. And sometimes star is also written as H. And we commonly represent them together by dagger notation. So there is no standard like rule that you have to use this or that. This is just notation. And normally when we write research papers, we just clearly specify them. Okay, dagger represent this or star represent this. So it is always better to declare this before writing a paper or any article. Okay, so let's take a matrix Q as a rotation matrix, say cos theta minus sin theta, and cos theta. Can anyone just quickly check that Q transpose Q? What is the answer for this? Don't look at the definition, just do by hand. So it will not be one. This will not be one. This is a matrix times matrix. It will be another matrix. This is the identity matrix. Yeah. So basically, your trigonometry will be revised again. So the component will be cos square theta plus sine square theta. Here it will be sine square theta plus cos square theta. And in this two particular case, there will be minus cos theta sine theta plus sine theta cos theta. And similarly here it will be your minus sine theta cos theta plus sine theta cos theta. So it is equals to identity matrix. So any matrix A is an ordinary matrix. Okay, A is an ordinary matrix. And the dimension of this matrix, say, are m cross n, some m cross n matrix. Okay. So I'll be interchangeably for next 1 hour. I'll be talking about various matrices. Like ordinary matrix, submission matrix. Already I have defined 2 more matrices, orthogonal and unitary, and we'll look at some other matrices as well, positive, semi-definite, and other things, and their properties and decompositions. So for now, if A is an ordinary matrix, then this particular matrix can be decomposed as a orthogonal matrix times a upper triangular matrix R. So where Q is your Q1, Q2, these are all the orthonormal basis set, like orthonormal basis vectors, these columns. Okay. Times a upper triangular matrix. That means so you will have elements only in these portions and rest all are 0. Okay. So this particular decomposition is called the QR decomposition. Now there is a natural question how to get these QR decompositions, right? So I'll not derive the thing, but I'll show you how to do these things with an example. So given an ordinary matrix, to get a orthogonal matrix and an upper triangular matrix, so the method normally we use is called the Gram-Smith method. Gram-Smith method. So there are other methods, but this is one of the most popular method. So it gives A to Q, okay, and times R. So how to do these things? Sorry. Let me get some space here. So how to do this thing is that when you have an ordinary matrix A, and the component of the ordinary matrix are like vector A2 up to AN, right? And this vector may not be orthogonal. Okay, they may not be orthogonal. That means A1 times A2 inner product may not be equals to 0. That means that vector, they are not like this. They can be something like this. A1 and A2 can be something like this, but I have to prepare from A1, A2 to Q1 and Q2 up, by doing some transformation such that Q1 and Q2 are orthogonal. So that is the main objective here, right? So what it does is, this procedure is that first you take this first vector as a reference vector, A1 vector, and you do the normalization A1 vector by norm of A1 to norm. So you will be getting some vector, you call it as a Q1 vector. Okay. Then what we have to do? Then we have to do the second vector as a orthogonal to this vector. I mean 90 degree, right? So to do that, so for j equals to 2 to n, you do a mathematical operation called the projection operation. I have a detailed video on 3 important operations. One is called the projection operation or mathematical projector, then reflection, and third is rotation. These are 3 basic linear algebraic operations: elementary projection, elementary reflection, and elementary rotation. So I shared the YouTube link that I recorded earlier, so you can have a look at that. So you do the projection operation, and what you get is that it's basically you design some say some vector uj that is equals to aj vector, which is an element of the matrix capital A, minus sum over aj. You take transpose or dagger, whatever you want to take. So I'm taking the dagger notation, aj dagger qj divided by qj norm for normalization times qj. And suppose your j equals to 1 to n number of elements you have, right? Then if we do that, whatever we get from there, we have to get back the qj as the normalized form, and that qj will be equals to uj by uj norm. So this is just I'm doing from the like coding format. Okay. So let's take an example to appreciate this concept. So suppose let's take a matrix A, and that A is 1, 1, 2, 0, right? So what is my first vector? First vector is 1, 1. And what is my second vector? V2. Second vector is, say, let's take it is A1, and let's take it is an A2. Okay. A2 as 2, 0. So So from here, you can easily get Q1 vector, which is 1 by square root 2, 1, 1, right? This is the normalized vector. Now, what is my, how to get the Q2? So basically, let's define some U2 as 2, 0, like this vector, minus projection of A2 on Q1. So if you just A2 is basically 2, 0, and Q1 is basically this one. So let's take a dot product of these two part, and then we should get something like this 1 minus 1. Just do a dot product here, okay, and normalize it. So then Q2 will be just a normalization of this vector, 1 by square root 2, 1 minus 1, right? So then what will be my orthogonal vector? So then basically Q will be Q1 and Q2. So that is equals to, and let's take 1 by square root 2 outside. So because this is common, so it will be 1, 1, 1, minus 1. So this is your Hadamard matrix, right? So you derived a Hadamard matrix out of a simple ordinary matrix just by doing the QR factorization. So, and similarly, you can compute the R. R is basically, you can see it is Q transpose A, right? So there is a way also to compute the component of R, Rij, that is the element of R, which is basically equals to the same formula I will be using, Qi transpose Aj. So this is the formula for this, right? So if you use this formula, so this is just a dot product, right? Simple dot product. So you take star or you take transpose based on the elements. So here all the elements are real. So I take the transpose part. So you'll be getting R equals to square root 2, square root 2, 0, square root 2. So the calculation is not the important thing. Your computer will be doing this. But what is important is that why shall we do the QR decomposition? What is so important here? Why shall we study this thing? So with this question, so let's revisit something called the pseudo inverse formula that yesterday we have learned about it. Pseudo inverse of a matrix, right? Pseudo inverse of a matrix. And in that particular case, so suppose what was the formula for that? The formula was A dagger. So that is the pseudo inverse of a matrix, A dagger, that is equals to, say, A star or A transposition of A star A whole inverse A star. This was my formula, right? And if I want to solve some equation X equals to B, where A might not be a square matrix, A might not be a full rank matrix. So what are the difficulties? If it is full rank, fine, you can calculate X hat equals to A inverse B. But if A is not full rank, or if A is simply a rectangular matrix, so we have to go for the least square solution, right? So in that case, your X hat will be pseudo inverse of A times B. This is the solution, right? Where pseudo inverse in this, yesterday I have covered 3 particular cases, both sided inverse, left sided inverse, and the right sided inverse. Take any one of them, just take this particular formula, right? Now you see how many matrices I am multiplying to get the solution of X hat, unknown variable. 3 matrices, 1, 2, 3, right? And if I want to do that, each such matrices, it is an ordinary matrix. There is no structure. There are ordinary matrix means, suppose, for example, there are n cross, it is suppose n cross n matrix. So that means there are n square elements, right? So if you want to multiply three matrices with n square elements, the computational complexity is so high, right? Because individually, if you even multiply, that is n to the power 3. So this is a computationally burden, right? Now what we have learned is that A equals to QR, right? So Q is fine. Q is a like a n cross n matrix, obviously, a orthogonal matrix, but R is an upper triangular matrix. Upper triangular matrix. That means already half of the things are almost zero. Only I have to work on these elements because this part is zero, right? So that means half of the effort is already reduced here. So then let us compute this part. So what is my thing like A star? A star will be QR star, right? So that is equals to R star Q star, right? So now if it is the case, then what is A star A? A star A is basically R star Q star Q into R, and Q star equals to identity matrix. So you are left with R star R because this is identity, right? Now what is A star A whole inverse? That is equals to R star R whole inverse, right? That is equals to R inverse time R star inverse, right? Now my formula becomes A dagger becomes A star A whole inverse A star, that is R inverse R star inverse R star, then Q star, right? Which is basically this part is again identity matrix, right? So you are left with only R inverse Q star. Now you see earlier three matrices I have to multiply, and individually they have n square elements. Now I left with only two matrices where this is n cross n matrix, but this is also n cross n matrix. But how many non-zero elements are here? Half, almost half. And there are n square elements. So there are n square non-zero element. There is roughly n square by 2 non-zero element, right? And I just need to do multiplication of two matrices just to compute the A dagger. So this is the method. Sorry. This is the method used in MATLAB software to compute the matrix inversion problem using the least square method, least square estimation. Uh, least square estimation. Now, why I am calling least square? Why the name is least square? I'll explain next week in the probability session. There is something related to probability error and all. Okay. But from the point of linear algebra, forget this word least square. This is simple a matrix inversion problem. Okay. And you can see the computational effort is much less here. Right? That's why QR factorization is so important. And I am not giving any more examples here that is given in the note. Right. So similarly, so any questions so far? Let me know. I'll go for the next topic. Is it clear? Like, can anyone just comment? Yeah, thank you. Okay, there are some more decompositions. I'll not cover all of them. I have given in the notes. I'll directly go to the EVD SVD, but I'm giving the essence where a particular formula is used with what computational advantage. What is the question? What is the importance of dagger? Okay, Dagger is just a notation. This is symbolic notation for complex conjugation or the simple conjugation. So it's just a notation only, mathematical notation. So there are some more factorizations. I am giving some review of them, and then I'll directly go to two important factorizations. One is the EVD and one is SVD. So before that, now there is a decomposition of the matrix A to LU. Okay. So LU decomposition, how to get from A to LU? This is everybody knows. So we form a equivalent form of this matrix A, and then basically we solve it through Gauss elimination method. So what we are left with is basically something like this. So there is a lower triangular matrix and there is an upper triangular matrix. So lower triangular matrix has all elements here, but this side is 0. And upper triangular is this side, all the elements are here, this side is 0, right? So this is roughly half of the elements, there is half of the elements, right? So this is one important this is this is for any ordinary matrix, for any A, this is possible. LE factorization is possible even if A is a rectangular matrix for any R M cross N. You can take C cross M Mn as well. So better to write in this form, M cross N. So I covered both the vector field, the real vector field and the complex vector field together as F. Okay. So basically this covers both the space R and C. So now M cross N and M cross N. So now there is one more factorization. That particular these kind of algorithm are used normally for basically back substitution based solution. Based solution, and often this is used in linear solving equation, linear solver problem, solving linear equations. So I have given examples in the notes. You can have a look. There is one more factorization. So this is called LU factorization. There is something called a polar factorization. So these topics I am not giving any details. So because the quantum application is much less in this site, but you can explore to discover. I don't know. What the quantum computing literature more and more concerned, the EVD SVD part, I'll come slowly. So a matrix A, so in this particular case for any matrix, but in this particular polar decomposition, A should be a square matrix. So this is the first constraint I am putting, square matrix. Means n cross n. Okay. So for the square matrix, this decomposition is validated, and possibly you can take a complex square matrix as well. The polar decomposition A equals to U times P. So what is U and what is P? This U is called, here it is unitary matrix. Unitary matrix, and this P is a PSD matrix. The full form of PSD is positive semi-definite matrix. Semi-definite matrix. What is the definition of PSD matrix? Is basically if you have any vector x such that x star px, right, equals to greater equals to 0, right? This is called a positive semi-definite matrix. And all eigenvalues of these positive semi-definite matrices are non-zero eigenvalues. Okay. Now I haven't defined what is eigenvalues. I'll come. Okay. So basically, if you have any ordinary matrix, you can represent to QR for any ordinary. But if A is square, you can better represent by UP. So where Q is your orthogonal matrix, R is upper triangular matrix, U is unitary matrix, P is your PSD matrix. These are decomposition. So sometimes because quantum operation are unitary, so this kind of operations like any generic, like if you have a better, say, better way of decomposing a matrix into unitary times PSD, and that unitary you have a quantum circuit for that. So in that particular case, these are useful, but P matrix PSD, we do not know the direct application in quantum computing. Maybe if you do this U part in quantum system and P part in the classical system. So for PSD matrices, there are very efficient, there are good efficient solution, classical solution, efficient classical solution. So if you have something U that is better solvable in a quantum computer, but if you have a P that is a better solvable in a classical solution, that means if you can break a matrix into a quantum plus HPC setup, like high performance computing setup, and you are fine to compute some properties of U through quantum computer and some properties of P through the classical computer, in that settings might be useful. I do not know the example for this, but this can be happen, right? So this is from my understanding I'm explaining. Now, why I say that PSD matrix can be efficiently solvable in a classical system, because if they are positive semi-definite matrices, so they have a decomposition called the LL star, and this particular decomposition called the Cholesky decomposition. Cholesky decomposition. That means what? Now P is suppose P is an ordinary matrix. So how many elements are here? There are n cross n elements, n square elements, right? Now L is a lower triangular matrix. That means half of the element you need. So this is half of the elements, roughly half of the elements, approximately, right? So you already designed some L which is containing half of the element. So you need not to compute again L, because you already have that memory. This L is it's already saved in some computational memory, right? So you can reuse that and you can compute a decomposition of the matrix in LL star form. So this heavily reduce the computational cost. Now I say heavily. Now what is that? Let's quantify that amount. So this is another decomposition. Oh God. So roughly Cholesky decomposition, roughly 1/3 n to the power 3 is the computational complexity to do this decomposition, which is less than LU decomposition. LU decomposition takes 2/3 n to the power 3 computational flops. Okay, these are the flop counts. And this is slightly better than QR factorization. QR factorization roughly takes 2 into n to the power 3 flops. But the ordinary way of computing QR using the matrix projection method is 2 to the 2 into n to the power 3. But there is a slightly better way by using by using the projection method. There is a slightly better research paper where people have shown if you use the householder, means mathematical reflection operator, then this complexity is roughly equals to 4 by 3 n to the power 3, which is almost equals to 2 to the power 2 into n to the power 3, but slightly better than that. But of course, QR is more complex than LU, and LU is more complex than Cholesky. Now you can ask me, then I should always use the Cholesky decomposition? No, because Cholesky only validated for PSD matrix. And then LU is basically via the Gram-Schmidt method, right? Or the Gaussian elimination method, and they have some stability issue. Then QR factorization is bit complex, but it is more stable. Yes, FLOP stands for floating point operation per second, correct? How floating operation calculus perform in 1 second? How many floating is correct? So now So these are several decompositions. So if you have any question, I'm pausing here for 2-3 minutes before going to the next part. That is the eigenvalue. I mean, the most important part. So I'm pausing here for 2 minutes. So you may ask questions till now. So I'm not giving the rigorous proof of all these decompositions, but showing their importance from the computational point of view and where they should be used with what conditions, right? So now let's talk about the eigenvalue problem. And I will say that this is the most important topic for quantum computing, even quantum physics. Uh, so I probably took some session in QT1, maybe 15-20 minutes. If you see the recording, so I have shown that if you take any wave function, right, and you apply an operator, right, and you get a quantity A times psi. So this is a matrix, this is a scalar. And if you are interested to calculate the energy of the system, if you want to calculate the position of a particle, if you want to calculate the momentum of a particle, if you want to understand the frequency of a wave function, so all these are the scalar quantities. I won't say scalar quantities. They are in fact eigenvalues. They are the eigenvalues of some operator. Of some operator. So operator is basically matrix. Okay. Of some operator, right? Which acts on the wave function that describes the quantum mechanical phenomena. Okay. So if you want to get your energy, what is energy? Energy is basically h nu, right? Or h bar omega. This is your energy quantity, right? So in fact, this is the eigenvalue of some operator. And that operator is called the energy operator, which acts on the wave function and gives you that eigenvalue, right? This is so important, or sometimes yes, called the generator. Okay. And that's why any quantity you are interested to calculate, any physical quantity, not necessarily for the physics. In fact, if you want to calculate the frequency of a signal, right, or any other physical quantity, so you need to go back to a quantum operator. You have to design a quantum operator or a matrix out of that. That operator, if acts on the wave function that describes your system, then the eigenvalue of that particular operator is the desired quantity you deserve. Okay. So this is why, like, you have a Hamiltonian operator. It acts on the wave function psi, and it gives you back the E energy times the wave function. And this is the solution of the Schrodinger equation. So what is this? This is basically eigenvalue equation. Now let us discuss what is the physical interpretation of this equation, why it is so important. Now suppose there is a vector and that vector is x. Okay. So yesterday what we have seen, that if I have a matrix, if I have a vector A And if I apply a matrix, say a matrix capital A, so what it does is basically does a linear transformation of the vector, and you get another vector, maybe vector B, because it can change what are the things it can change the rotation, it can add angle, it can change the amplitude of the vector, right? So or the shearing of the vector. So these are the things it can perform, linear operations, right? But if you find a matrix A and if you find a vector X, I'm writing the KTX format, that's okay. But instead of changing the angle, it will only stretch the vector. It will only stretch the vector either this way or this way. So basically this will perform a scaling effect, right? Say, for example, if you have a rotation matrix, say 0, 1, 1, 0, Pauli rotation, Pauli X, right? So what it does is basically from here to your x-axis rotation, right? If this is your x-axis, basically it will rotate from here to here. So you'll be reaching here at this particular point, right? So this is not stretching the vector, but this is changing the angle, right? Theta equals to 90 degree. This is changing the angle. But in this particular case, if we find a, so this is basically Pauli X matrix or Pauli X operator. But if we find a vector X such that if I multiply A times X, I can only stretch that vector with little a amount. So this is the amount, whether it is twice of X, or it is half of X, something like that. So what is changing? Only the scale is changing. This is basically scale. Scale scales the vector. So that means it does not change the direction of the vector, only it changes the amplitude of the vector, right? So this particular thing is that's why. So now this vector ktex, if I take non-zero such vectors, then this set of vectors are called eigenvectors. Are called the eigenvectors. Now, what is the thing is happening? So if I can find the eigenvectors of a matrix or a system, okay, then basically I can find out those vectors which will give me all the stretching that can better represent the matrix in represented in the vector space spanned by the eigenvector. So what is that? So basically earlier my matrices was what? A2, these were the column vectors, and I do not know whether they are orthonormal or not or what, right? What I am doing, I am just multiplying with a vector. Okay, just let's take a single vector. Let's take x0, x1 to up to xn, and this is entirely at x bar. Okay, and this part is a. Okay, so this is same as x0 to xn times some amount, scalar amount a. So this entire matrix is only stretching this vector and doing nothing, right? Now the question is, if I find many such vectors x1, x2, x3, so I can form some equation like a x1 ket equals to say lambda 1. Instead of a, I am writing as lambda 1 x1. Then a x2 equals to lambda 2 x2, so on up to a xn up to lambda n xn. If I can find n such possible vector, n such possible vectors which are orthonormal to each other, okay, then the set rho of a equals to lambda 1, lambda 2, up to lambda n is called the spectrum of the matrix. It's called the spectrum of the matrix. Spectrum of the matrix. Now let's go back. Earlier I have the equation H psi equals to E psi, right? Now I can find many such psi, like suppose I can represent this psi in the computational basis, right? So computational basis is what, like C1 ket say, so ket 0 plus C2 ket 1 plus C3 ket 2 and so on. Or in general you can write Ci ket I in this way. You can input the wave function in this way. You can also represent this wave function into this way, sum of lambda I and some ei, okay, over I, where ei are the eigenbases and lambda I are the eigenvectors. Same thing, because it obeys the superposition principle. Now these ei are the orthonormal basis set. There is no problem. So earlier I started with some arbitrary wave function, right? So first I will start with some arbitrary wave function. I do not know that this is the wave function which will give me the exact quantity that I am interested or not. But I can always represent any arbitrary wave function in the eigenbasis, in the computational basis, similarly on the eigenbasis, some lambda I times ei. If I can do that, then I can estimate all this lambda. These are the desired quantity. Right. So basically, if you find the minimum of your rho sigma, rho A, right, that is equals to your lambda mean, and this is the ground state energy of your system. Right. Okay, there are some questions. Let me take light cones in Monosky space. I don't know. It is asking. So I'm not talking about a particular space, whether Minkowski or the Banach space or the Hilbert space. This is just a simple basis expansion. Okay. Okay. So that means if I am interested about a physical quantity, so I should find the eigenvectors. I have to find the eigenvectors and the particular operator A, and the eigenvector, say the eigenvector is E, right? If I can find these two things, then easily I can find out that quantity lambda. So if this equation is satisfied, then I can easily get the desired quantity. So if this A matrix, if it is your Hamiltonian operator, then lambda is your some discretized energy. So that's why now the question is, okay, fine. The question is, when shall I be able to do this, right? Is it always satisfied? So I have to check whether I am able to find all such E vectors which basically satisfies this equation, right? So now if I want to get, because physical quantities are real, physical quantities like energy, momentum, all these are real quantities, right? These are real quantities, real scalar values, right? Say for example, your energy is this much joule, momentum is something, your position is some meters, some centimeters, right? So they are real quantities. So that means if you want to get the eigenvalue lambda, that is a real quantity, mathematics says that if you want to get that, then A has to be A star equals to A. It has to be a Hermitian matrix or the symmetry matrix. Symmetric or Hermitian. That's why all the physicists use only Hermitian operator in order to get real quantities back from the system, right? But in general, if A is not A may not be Hermitian, that particular case, lambda may be complex. Okay. So this is the problem called the eigenvalue problem, and something that I have also defined that is called the spectrum of a matrix. Okay. So now I'm pausing here, and then I'll continue the eigenvalue decomposition from this point. Okay. So if you have any question, you can write in the chat box. I'm getting some problem. Okay. So now there is something more called the geometric multiplicity, arithmetic multiplicity and all. I'm not covering those details. So that is already given in the notes you can look at. Now uh, let us start something called the eigenvalue decomposition. And so first, let us understand that when the eigenvalue decomposition is possible. Okay. So we'll come to that point. So let's take a square matrix A. So which is n cross n matrix. And this A matrix can be represented as U lambda U star. Okay. So where U is basically the unitary matrix and lambda is a diagonal matrix. Now for the first time we are basically so A was an ordinary matrix. So computationally, how many elements are here? N cross n elements are here. Now from here, we are going to some diagonal matrix, which is also n cross n matrix. But here, at most, I have n square non-zero element. Here, I have only n non-zero element. So earlier, I have, if I want to do anything like matrix multiplication, inverse, or anything, so I have to do everything on the n square elements. So computationally not efficient. But now I just need to do anything on the only the diagonal elements part because rest are zero. So this is basically this looks like this lambda looks like this lambda 1, lambda 2 up to lambda n and all rest are zero. All rest are zero. So when you will try to compute matrix inverse, so forget about this U and U star thing. They have to do other business. But this lambda matrix is so important that if you just want to do matrix inverse, you just better do on the lambda inverse. And instead of like when we learn the matrix inverse method, even it is a 2 cross matrix, 2 matrix, we need to do so lot of things, calculate the determinant and many other things, right? But here you only need to do these things. Lambda inverse is just 1 by lambda 1, 1 by lambda 2, that's all. Now, so let's take. So there is Still some issue. Just please allow me a few seconds. Ah. So suppose A inverse, right? So now A inverse is basically your U lambda U star whole inverse, right? So we should be able to write this way, lambda inverse, and this is your U inverse, right? Something like this. Then so this is basically U star equals to U inverse. U inverse of inverse is U, right? And this is lambda inverse, and this is U star. So because the definition of unitary is U star equals to U inverse. Right? So just put these things here, so you'll be getting the same equation. So you just need to operate on the lambda. So that is some theorem, Cayley-Hamilton theorem on that. So I'm not going details of that. So if you can expand a matrix into the eigenvalue decomposition, you are not only representing the matrix in a most simplified version, that is the diagonalized form, but also you can take any function on A, and that will be basically operating on the lambda. For example, if you want to compute the A square of the matrix, you better do lambda square, right? So now square of a matrix, n to the power 3 operations, right? So basically element wise, if you do the A times A, so A square is what? A square is basically A star A, right? Matrix multiplication, right? So here you basically do U and lambda 1 square, lambda 2 square, and so on up to lambda n square, and it's done. So that's all, nothing else, because all this element are 0. So that's why this is so important, right? And now basically you can basically so there is a long derivation process. So I'm not going to that direction, but there is a short way of basically there is a shorter way of proving the theorem, and that I can show. So we just have learned that A times, say, kate eigenvector, say kate V equals to lambda times kate V. This is your eigenvalue equation, right? Eigenvalue equation. Now I can take many such V, right? So for example, V1 lambda 1, A V2 lambda V2, sorry. So there is a wrong way of using the notation. So we can rectify that. So V3 lambda V3 so on, right? So let's stack all this V. Okay. So what we get? We get so this is basically scalar time of vector is also a vector. This is a scalar times of vector, another vector, right? Similarly, vector scalar times another vector. This is another vector. This is just, these are just only scaling of the vectors, right? So now if we just stack all of them, then what we are left with? So A times, if we multiply A times with all these vectors v1 v2 up to vn, then what we are doing? We are doing lambda 1 v1, right? Lambda 2 v2, lambda 3 v3, and lambda n vn, right? This is what we are doing. So this is together as a vector, together as a vector, together as a vector, right? So now you call this as a bigger matrix, say A times V. Okay, this is a matrix. So these are individually vectors, right? Now understand that this is part of a like a column vectors of a matrix, right? So A times B equals to, now you can represent this particular vector, we can write in this way. Lambda 1, lambda 2 up to lambda n times V1, V2 up to Vn. So basically, if you do diagonal matrix times a simple matrix, so basically this times V1 is this one, lambda 1 V1, lambda 2 V2, lambda 3. So simply row times the column multiplications, right? So row times column multiplication. So you'll be getting that one, right? So that means this is equals to the equation lambda, basically V lambda. So this is actually I have wrongly written. This should be coming this side, okay? Then only you can do the row times column multiplication, you'll be getting that. So this is a reverse, I have written in the reverse form. So this should be V into lambda. Now what I get, A V equals to V lambda, right? Now because the columns of the V are linearly independent, they are linearly independent, and V is an invertible matrix. So I can multiply like A times V inverse, because all the columns of the V matrix, they are basically independent, linearly independent. So I can post multiply with V inverse with the AV equation, and that is equals to V lambda V inverse, right? Okay, and in that particular case, this is identity matrix, and A will be equals to V lambda V inverse, right? And V inverse equals to V star for unitary matrices. So that's why you can also write it as V lambda V star. So this is a simple proof of the eigenvalue decomposition part, right? So instead of showing example, I will be showing MATLAB code for this and an example for image compression. Okay. So this is basically all about the eigenvalue decomposition part, and the major objective is basically going from n cross n element or n square elements to n elements, which is computationally very efficient. That is the computational benefit part. And quantum computing, any basically, so what we do is basically in quantum circuit, you will be seeing that you are doing the measurement, quantum measurement, right? To quantum measurement to get the classical information back from the quantum state some phi. So you start with some psi 0 and you apply a quantum circuit, right? And you get some final quantum state, then you do the quantum measurement. So what you are doing in the quantum measurement, there are various computational bases, right? Say triple zero to triple one. There are say 8 computational basis set. Now you can say these are computational bases. Okay, these are the computational bases for Pauli operators, but these are the eigenbases for G operators. Let's take an example. What is the definition of G operator? So G is basically your 1, 0, 0, minus 1. Probably in the quantum information theory, I have covered this, but I'm repeating again. Suppose your computational basis is Ket0, right? So G times Ket0. So what you will be getting? So simply multiply it. So 1 times 1 is 1. And basically all this touch 0, basically 1, 0. So you are getting Ket0 back. So that means your eigenvalue here is what? Eigenvalue lambda equals to 1, right? Similarly, if you apply Ket1, you will be getting minus of Ket1. So that means your eigenvalue is minus 1. So that means you are basically applying this Ket0, Ket1, and all these are as an eigenvector of the operator G, and you are getting the eigenvalues plus 1 and minus 1, right? Whether the quantum event is happening or not happening probabilistically, right? And you are counting how many times it is happening. Based on that, you are calculating the probability of occurrence, right? So that means they are typically eigenvalues, right? So from the eigenvalues, you are getting the result. So that's why many cases you will see that when you design the quantum circuit, you are effectively using many of the G gates, right? Such that you try to get the eigenvalues of the G operator through the rank 1 measurement or the quantum measurement that is available in Qiskit. So there are in physics, there are various other measurement scheme, like for example, POVM operations and all. But in general, in the quantum computing, you normally do the measurement on the computational basis, which are the eigenbases for the G operator. So that's why it's so important. And I am stopping with this EVD thing here, and I will pause for 5 minutes just to for the next recording lecture. And in the next lecture, we'll see some programming to see EVD and SBD. So I'll cover the SBD first, and then I'll show the programming stuff. Yeah. So any question you can put it there. Capital V is a matrix, little v is a vector. Okay. So here this capital V is basically the elements are little v vector, v2 vector, v3 vector, and so on, vn vector. Okay. So I have stacked them. The only condition that I haven't shared here, the only condition to compute the eigenvalue is that for any ordinary matrix A, eigenvalue decomposition may not exist. Okay, so it will only exist for the normal matrices, even if they are not directly solvable. So normal matrices are A transpose A equals to A transpose. If this condition is satisfied, then only you can apply EVD on A. This is the condition for eigenvalue decomposition. Now Hermitian matrix is directly follows this equation. Like A say A or I can write A dagger A equals to A dagger. So that simplifies both the transposition and the Hermitian operations. Right? Please explain the interpretation of G operator and resultant. So what is G operator? G operator is just a matrix, right? And all the computational basis. So basically this Ket0, Ket1. So basically, let's take these two computational basis. So right, and you have a two-level quantum system. Simple psi is basically alpha times your 0 plus beta times 1, right? And you are doing the quantum measurement in order to retrieve over many iteration what is the value of alpha square and beta square, right? That's what our objective is. So basically, if we project on the Ket0, we should get basically the alpha, and if we project on, so basically psi times 0, if you do the dot product, and 1 times psi, if you do, you get the beta, right? So simply because 0 times 0 is 1, that means 0 times 0 dot product into alpha is alpha, and 0 times 1 is 0 times beta is again 0. Similarly, 1 times 0 is basically 0 because they are orthogonal to each other, right? Orthonormal to each other. So this is basically 0. And if it is 0, then basically you are getting alpha equals to also 0. So after multiplication, then 1 times 1 is 1, and you are left with beta, right? So alpha and beta. This is the objective we are trying to get. So basically the probability will be alpha square and beta square, means square of this norm, right? But how to get this? So basically, so G operator is basically so basically I have to check whether Ax equals to lambda x or not, right? So if I apply the G operator, G matrix, and my eigenvector is Ket0 vector, so that is basically your 1 0 0 minus 1 and 1 0, and what we are getting, we will be getting same value 1 0. That means here there is 1, right? So here lambda equals to 1. Similarly, if we apply this one thing, 1 0 0 minus 1, and it is your 0 1, and it is equals to your, it will be your 0 1 minus. So that is basically minus 1. So times this, so lambda equals to minus 1. So these are the eigenvalues, right? So basically, if this equation is satisfied, that g times 0 equals to 0, right? That means, so if I do on the g basis measurement, so then basically I get the further measurement will not impact it, right? So that's why basically because computational basis are the eigenbasis for the G operators. So that's why we can measure them and count how many times it is coming. This particular basis is basically coming because if you find the eigenbasis of a quantum state, so by doing repeated measurement, so basically your quantum state will not change, right? It will give the same value again and again, right? And you measure how many times it is giving you on the frequency, right? And that will give you the probability measurement. So you repeat n number of times and you see that Ket0 is repeated n1 time. So this is the probability alpha score. Sir, will you be giving break in something? Yeah, sure. So break for now and we'll come back again with the SVD in 5 minutes.